Hello everyone, welcome back to Calculus 3. In this part, we are going to study 3.3 arc length. Actually, I really want to say this is really not a totally new material. We have this type of topic covered in Calculus 2 already. I hope you remember this formula in Calculus 2. When we have a curve using the parametric form, and indeed the arc length can be calculated using this fashion. In the parametric form of a curve in the two-dimensional space. Okay, and now I hope you understand the parametric form can be considered as a single vector-valued function. So R of t, it is of x and y, that is a vector-valued function. And indeed, if you separate x and y, they just tend to be the set of parametric equations. So it's really not new. And furthermore, in the three-dimensional space, the arc length can be calculated using this fashion, similar fashion, because in the three-dimensional space, a curve has three components, right? The vector value function has three components. So accordingly, it would be the integral of the square root of x prime squared plus y prime squared plus z prime squared. This is the arc length formula. And again, as I'm saying, it's really not new. It will serve as a very good review topic, not only for arc length, and also some basic integration techniques, like integration by substitution. Okay, so this is the example I took from the textbook, checkpoint 3.9. It's find the arc length. It's given by this function, and the t, it is a parameter. T, it is a parameter. T changes from 0 to 3, 0 to 3. Okay, so in this case, this is what I did, my calculation. I tried to write down explicitly x of t. It is the first component, x of t, and then y prime of t, y of t, then z of t. I take out each component directly, and then calculate the derivative. So x prime, it is 4t, and the y prime actually turns out to be 4t again. Then z prime, it is 3t squared. And using the arc length formula, this is the integral we should consider. And I already calculated the derivative of each. So I copy down this integral, and the t is changing from 0 to 3. X prime, it is replaced with did I miss anything here? X prime, it is replaced with 4t. Should be 4t actually. Yeah, this should be 4t. And this should be 4t. I believe z prime should be fine, right? Z prime should be fine. And then this is 4t squared, 16t squared. There's another same item. So really this should tend to be 32. 32. And this part, it is 9 times t to the 4. And also I hope you can tell t squared, t to the 4. T squared is a common factor, right? So we can take out a t, take t squared outside of square root notation, that tends to be t. Inside, we are having this should be 32 plus 9t squared. And then to consider this integral, this is what I said earlier, you need to consider integration by parts. So using integration by parts, accordingly, you should take u as 32 plus 9t squared. I hope you see du, it will cover t and dt together. So indeed, this really will tend to be 118 du. It is 18t dt. So t dt together, it is 1/18th of du. Just to save some writing, I did show you the idea of substituting here. But anyway, in the actual writing of the integral, I'm trying to keep this in terms of t in its original form. Okay, I'm seeing this as u. This is in together. Actually, this should be 32. That's u, and this part is the square root of u. Square root, when we consider antiderivative, it is always considered as u to the 1/2, u to the 1/2 du. So using the anti-differentiation power rule, this 1/18 still stays u to the 1/2. 1/2 is increased by 1, tends to be 3/2. Then the reciprocal of 3/2 right before u. This is u, okay, before this u. So that tends to be 3/2. I believe this really should be 2/3, right? The reciprocal of 3/2, it should be 2/3. And then this really should be calculated as 1/27, 1/27. And this is 32. And this is 32. And this should be 1/27. And the answer, this should be 1/27. And now let me see if this will cause any bigger changes. 3 squared, that's 9. 9 times 9, that's 81. 81 plus 32, I think that's 113, right? 113. Let me verify the calculation. It's 81 plus 32. That's 113. 113. And then minus, replace t with 0. So this part tends to be 0. And I think I'm having this as a 64. I don't know. It should be 32. 32 to the power of 3/2. 32 to the power of 3/2. Probably it can be simplified. But anyway, I think I'm just going to keep this as in the original form here. See. So this part should be 32 to the power of 3/2. I think this should be it. So for section 3.3 about the arc length, if you want, you can say there are two formulas. One it is for the two-dimensional case, the other it is for the three-dimensional case. But anyway, they are really the same. They are really the same. I hope you see that. And especially do give a try how you handle an integral with square root, And usually it is hard. So the example I showed here, it does require the technique, so-called integration by substitution. I hope you still remember the technique and you can handle it very well. And if not, let me know. Hey, thank you for watching. I'll see you next time.